Just to justify the direction of the centripetal acceleration, think of it with vector addition. Okay, so we got an object going around clockwise. At one instant, it's going in that direction. The next instant, it's going in that direction. If we do delta v to find the acceleration, just to find the direction, right? V minus v0. So v plus negative v0 tip to tail, we end up with a delta v that's in that direction. And I've just done approximates on that. But basically what's happening there is the average velocity is towards, the change in velocity is towards the center of the circle. And again, I've just done really rough things, but just to justify the fact that change in velocity and therefore acceleration have a direction towards the center. We're going to talk about uniform circular motion. Uniform circular motion is when an object is moving in a circular arc and at a constant speed through that part of the arc. So, vector notation, you got the v with the arrow, and they put the magnitude of that. We're going to just use v, plain v, so the speed of the thing, because that force and the acceleration depend on that speed. It's moving in a circular arc. It can be just a part of this. It's really, like a car turning a corner, something like that. It doesn't have to be going in a circle. One of the definitions we're going to need is period. Capital T, it's not little t is time. So capital T is the time for one revolution or one trip around that circle, and that's in seconds. We also need to learn the word frequency. Little f is the symbol, and it's revolutions per second. How many times per second it goes around. You don't always see it in revolutions per second. You can see it in 1 over seconds or seconds to the -1 you'll see sometimes. Hertz is the main term that we use, the main unit we use that. Hz is hertz. So it'd be things per second as we see when we do waves. Frequency is just the inverse of the period. Period is time for one revolution. Frequency is number of revolutions per second. So in this case, if we have an object moving around a circle of radius r with period t, find the speed, find the magnitude of the velocity, and pause if you need to do that. And the way we do this is if we know the time it takes to get around, that's how long it takes to go one full circumference. So if we have r, we can find the circumference, 2 pi r, that's how far it goes. The time is the period. So the magnitude of the velocity is 2 pi r over the period. And I'm putting that in there because you use that quite a bit. Now let's talk about the acceleration and indeed the force on an object moving in uniform circular motion. The picture I have here is of an Olympic hammer thrower, and he spins around with this heavy weight at the end of a cable, and he moves that around him in a circle. And you can see, if we do a free body diagram for that object, there's going to be mg pointing downward, but in the plane of the rotation, there's really just that tension, okay? And, air resistance, but basically that tension is towards the center. So therefore, that net force, when we think of the velocity as moving tangentially, at any instant that thing is moving tangent to the circle. And to make it turn, if we didn't have an external force, it would just keep going with the same velocity, right? But we want it to turn. We have to exert a force, a net force towards the center. And in this case, that net force is provided by the tension. But, when we have a vertical circle, it gets a little more complicated. We'll see that. Well, if the net force is to the center, net force equals ma, so the acceleration also has to be towards the center. We have a special term for that, the centripetal acceleration. Center seeking, centripetal acceleration. We call the net force the centripetal force. And so that net force is what causes that acceleration. And the equation we have for this that I'm not going to derive is the centripetal acceleration is v squared over r, the speed squared, or the magnitude of the velocity squared, divided by the radius. So if we look at Newton's second law, the sum of forces is m times the centripetal acceleration. We plug in v squared over r, so we have the sum of forces m v squared over r. Okay, this is the total acceleration because we're talking about uniform circular motion where the velocity doesn't change, but the velocity could change. In fact, very frequently the velocity does change. Think if you're a car stopped at a light and you're taking a left-hand turn, your speed is going to change and you're going to turn. In this part of the unit, before we get to rotation in a later unit, we're really just going to be talking about the rotational acceleration. There's the centripetal acceleration. That is the acceleration that just makes the thing turn. Okay? So at any instant, there's going to be this acceleration towards the middle. But if you're speeding up or slowing down, there's also going to be a tangential acceleration. So later on, when we get to rotation, we're going to have centripetal acceleration, the acceleration of turning, and tangential acceleration, the acceleration of speeding up. And when we have these things that are perpendicular, what we can do is we can use Pythagorean theorem to figure out the total acceleration. Again, this is just previewing that centripetal acceleration isn't the only possible acceleration in an object that's turning. We're going to be talking in this unit only about centripetal acceleration. Okay, we swing a ball on a string horizontally on a table with no friction. And again, there are going to be some forces there like mg and normal force that are not in the plane of the circle. We wouldn't see those if we're looking at the plane of the circle. If it goes around 3 times each second, find the centripetal force and the centripetal acceleration. Okay? They give us a radius and a mass. Well, the frequency is 3 times per second. So the frequency is 3 hertz. The period would be 1 over the frequency, so 1/3, which is 0.3 repeating. I've rounded it or truncated it. The velocity, well, we know the circumference is 2 pi r. The period is 0.333. Those two things agree. 2 pi r is the circumference. In other words, the distance once around. T is the period, and that's the time once around. So those two things have the same domain. And we multiply all that out, and we should get 13.19 meters per second. Centripetal acceleration is easy. It's v squared over r, 13.19 squared divided by the radius. And then the centripetal force is the sum of forces. That just equals m times centripetal acceleration. And that's 1242 newtons. This is an interesting one because we start getting to vertical circles. In that last one, the only force was whatever the force is towards the center. Here we swing a pail of water of mass m in a vertical circle, radius r, speed v. Find the force exerted on the water by the pail at the top. Find the minimum value of v for water to remain in pail. And find the force exerted at the bottom of the circle. Anytime you see a circular arc, I want you thinking about centripetal acceleration. Again, you may have to think about tangential acceleration also, but in this case we're not dealing with that. We just want the centripetal acceleration, the acceleration for the turning. So as soon as you see a circular arc, think, oh, centripetal acceleration. And it'll be clear why I say that in a moment. So here's at the top. At the top we have mg down, but we're also, if we're swinging it, let's say we've tied this bucket to a string and we're swinging it around. The water not only has the weight of the water pulling down, it also has the bucket keeping it from flying out. Okay, so it's exerting a normal force towards the center. Now, if we look at that, we have to define towards the center as positive. That's the way that v squared over r is defined. Towards the center. So we look, set up Newton's second law. We've done free body diagram, frame of reference. We do Newton's second law, sum of forces equals ma. And I will say, always substitute force things on the left, always substitute motion stuff on the right. It keeps things straight. So on the force stuff, I'm going to have normal force plus mg. On the right, that has to equal m times, substituting in for centripetal acceleration, v squared over r. Then we're just really going to find the force exerted on the water by the pail. That's the normal force. So that's just going to be normal force is mv squared over r minus mg. Not too bad. We'll see when we get to C how different it is at the bottom. If you think of that normal force, it's mv squared over r is how hard it is to turn that water in a circle, make it turn. But that normal force is helped by mg. The bigger mg is, the less normal force has to be applied to make it turn. So it's a smaller normal force. If we had no gravity, we just have mv squared over r. We had gravity, well, that's helping us make that water turn at the top of the arc. Now let's look at B, minimum value for V for the water to remain in the pail. Well, if you think of this, think of we just barely make it over the top. When you just barely make it over the top, that water, the pail's really not doing any work. The water kind of wants to fall, and so it's going to be actually kind of in projectile motion. If you think of it that way, it's moving to the left if we're rotating counterclockwise, moving to the left, and it's falling. The mg is enough to get it turning. So there's no force from the pail, it's only mg. Anytime they say barely get over the top or the minimum value of V over the top, what you want to do is just have that free body diagram that just has mg. If you think of the rope attached to this, it would go slack when it just barely makes it over the top. There's no tension pulling on that, so there's no normal force pulling down on the water. So we do our Newton's second law. The total force is just mg, and mg equals ma, so g equals the centripetal acceleration, v squared over r. Just canceled the m's out. Okay. The minimum value of v is going to be the square root of gr. I don't think I wrote that. Sorry about that. So v equals square root of gr. Now let's look at the bottom. At the bottom, you still have mg, but it's pulling down away from the center of the arc. Normal force is pulling up. It has to pull up much harder because it's opposing mg. Notice these two are not in equilibrium or the object wouldn't turn. So again, we see a circular arc. We've got to be thinking of disequilibrium. We've got to be thinking of an acceleration. So sum of force equals ma. We have to define towards the center as positive if we're going to use that v squared over r. The direction is defined as towards the center. So normal force in the positive direction plus negative mg equals mv squared over r. And when we solve, that normal force is mv squared plus over r plus mg. If you look at that a, we had it as minus mg. Normal force didn't have to do a whole lot of work. If we think of this as like a ramp where the motorcycle is going over a vertical loop, at the bottom that vertical loop has to do a whole lot, has to exert a whole lot of force to turn the motorcycle towards the center. At the top, gravity is helping, so the normal force doesn't have to be as big. Very important to understand that dynamic. Car moves 15 meters per second around a track of r equals 50 without sliding. Let's find the acceleration and minimum mu the tires can have. Okay, so it's really important to look at that free body diagram. There's mg. Then the only other contact is the ground, which will have normal force perpendicular, ends up being equal to mg because there are no other up and down forces and it's not accelerating up or down, and the force of friction is towards the center. It's static friction if it doesn't slide. Okay, we want it to not slide. If it's sliding, it becomes kinetic. It's weird because static friction, tires are moving, but they're not sliding relative to the surface. So tires generally operate on static friction. So let's take a look. Sum of force equals ma, and we're going to look at the, didn't draw it, but the left is going to be positive. Really bad habit not doing a frame of reference. Sum of forces equals m. Well, it's going to be moving in a circular arc, so v squared over r. The minimum mu. If we have a huge mu, we have a big maximum force of friction towards the center. We're trying to find that one where it just makes it without sliding. Okay, so a bigger mu, you could drive, if we look at that equation, if you have a bigger mu, you could drive faster. That v can be bigger. Or if you have a constant velocity, you could have a smaller r for a bigger force of friction, maximum force of friction. So we're talking about the max force of friction, which will be mu static times the normal force, mv squared over r. And then we solve this. Normal force is mg. The m's cancel. Mu equals v squared over gr is 0.45. This is an interesting problem. This is an amusement park ride where it's this circular room. It goes fast, 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 and then when it gets really fast, the floor drops out. So they're just hovering there. I shouldn't say hovering, they're pressed against that back wall, or more to the point, the back wall is pressed against them. They spin fast. So we'll draw a free body diagram and break this down. This is a tricky one because people screw up the free body diagram. So free body diagram for that guy on the right. It's got mg, of course. The only other contact is that surface. And that surface will have a normal force perpendicular to the surface. So the normal is that way, to the left. Force of friction ends up having to be up to cancel out the normal force, so you don't sink. So when we look at that in the x direction, sum of force equals ma. It's circular motion, so normal force equals mv squared over r. In the y direction, sum of forces equals ma. Well, force of friction is mu static, it's not sliding, times the normal force. And again, we're trying to find that minimum v. The minimum, if it's going slower, it would slide down, so we need that minimum v. We're talking about the maximum force of static friction. So mu s times the normal force minus mg equals m times 0. It's at equilibrium vertically. So we have that equation, right? But that normal force is going to be mv squared over r. So the v ends up being square root of gr over mu, and that ends up being 7.25 meters per second. Conical pendulum comes up occasionally. It swings out the surface of a cone. So you think of somebody doing a lariat upside down, something like that. This conical pendulum, this thing is going around in a circle. The pendulum bob is going around in a circle as it's going around attached to a string of length L. What's a little weird here is that theta. We usually have theta angle from horizontal. Here it's from vertical, so you got to be a little careful. So free body diagram's easy. mg, the only other thing is tension. That's easy. So we've got to have our frame of reference is going to be to the right as acceleration is to the right there when it's over in that spot. So we have to break that up appropriately. Okay. So ft sine theta and ft cosine theta. Remember, it's the sine of theta because it's the opposite of that angle. When we get in here, y is sum of force equals ma in the y direction. In the y direction, we have ft cosine theta minus mg, if we call up positive, equals m times 0. So we have the force of tension equals mg over cosine theta, 18.8 newtons. There's the tension. Now when we look at the x direction, if it comes up, there we go. Sum of forces equals ma. The only force is ft sine theta, and the acceleration is centripetal, v squared over r. So now we have mg sine theta over cosine theta, which is mg tan theta, equals mv squared over r. So we end up with v equals the square root of r tan theta equals 3.16 meters per second. R is, as we see in the middle of the slide there, L times the sine of theta. We needed that to get the dimension. Period, circumference over velocity, ends up being 2.68 seconds. Velocity is circumference over period. Period is circumference over velocity. Last one, vertical loop. Again, we did this before, but it's really important to be able to do this very easily. Okay, so free body diagram up at the top. Normal force is pushing down. mg is pushing down. We're going to call towards the center positive. F equals ma. Normal force plus mg equals mv squared over r. Normal force is 481 newtons. The minimum velocity to stay at the top, to stay on the track. Minimum velocity, once again, we're talking about barely staying on the track. If it went any slower, it'd fall off the track. There'd start to be a gap there. So it's only mg, sum of force equals ma. mg equals mv squared over r. G equals v squared over r. G equals square root of v equals square root of gr, 10.95 meters per second. At the bottom, once again, they're in opposite directions. I should have that normal force much bigger because it has to counter mg. It has to be bigger than mg. But the same thing we did earlier. Normal force minus mg equals mv squared over r. Normal force equals mv squared over r plus mg. Ends up being 1581 newtons. much bigger than the normal force for going over the top. At the top, mg's helping. At the bottom, mg's hurting.